Hello, everyone, in person or remotely. It is a pleasure to start this second day of activities of geometry, topology, and singularities in the Americas with stellar speaker, Anatoly Libgober, not only from the University of Illinois at Chicago. Not only he is a very, very good speaker, but he's legendary for his work in the interface between geometry as well as geometry and topology. And his work has been very influential in the mathematics of the Americas, especially in the school that studies the topology of orbifolds. His work has inspired many ideas and many interactions, and it's a pleasure to have him today talking about Braid, Monodromy, and Divisibility of Alexander polynomials of real singular curves.
Okay, well, thank you very much, Vanessa, for the introduction. It's a pleasure to be here again in Miami. I'm standing around for the doing something wrong. Let's see. Yeah, so it looks like it can be very informal talk. We have this very small audience here, so please feel free to ask questions. Yeah. But let me tell, well, I realize because it's also kind of not, it's somewhat distant from what most of you are speaking. It's recently. So, but it's this question which I want to address the main problem. It's rooted very classical mathematics and old problem that understanding fundamental groups of quasi-projective algebraic variety. So this is a very old problem. Many people work from different directions. So this is one. Well, study of Alexander polynomial. It's one of the way to study non-abelian fundamental groups of the components. Yes, so that's one thing, one way to think about this. So basically to, well, it was a standard Lefschetz theorem, so allowed to reduce this question about the quasi-fundamental groups of the well, I'm talking about quasi-projective surfaces, because it's as you the study of projective and quasi-projective groups are quite different. So what are quasi-projective groups? So you take a projective surface and then you remove some device. Okay, so and a fundamental group affected by, of course, fundamental group to the ambient surface, projective surface, and plus it's affected by divisor, which you remove. So, so what I wanted to focus only on this second part, the project of the removal of devices. So what kind of fundamental groups can pop up? Okay, and so the way since we want to approach this point, so one actually perhaps somehow understand not whole fundamental group, but invariant fundamental group. And Alexander polynomial is invariant fundamental group. And so what's interesting about Alexander polynomial that you actually can relate it to some geometric information about divisor and singularity. And this is important because one of the hurdles in all these problems about fundamental group, we don't really know what affects complexity of fundamental group. You know, but it's well, I'll mention a little bit comparison with knot groups, and there, of course, there's much more flexibility there. For instance, as study knot groups, it's much easier task in a way than study fundamental groups of the complement to divide. So but Alexander polynomial actually can relate to geometry, and so this the question which I want to address: which polynomials can appear as Alexander polynomial in algebraic curves? So that's a very simple statement, which polynomial. And it turns out there is a lot of restrictions. And so this question can be made much more specific, in fact, about possible value of single number. And that's what I'm going to explain right now. Okay. So, and what is new sort of in this stuff? So before, so just looks like complexity of Alexander polynomial come of local type of singularity, and how special their position. Whatever that means, I explained in a little bit how special position is singularity. So here, it turns out the presence of real structure also affect from the Monodromy group in actually quite specific way, or at least Alexander polynomial, very specific way. And so it turns out for real curves, one can actually give better bound on the degree of Alexander polynomial. So that's the main point. Well, okay, so oops. Okay, so now if you want more details about this, so this first paper is specifically with material of the stock, and second paper is just a survey paper for handbook and singularity about Alexander polynomials, and and the third one is also so just where actually first time this idea which comes in first work.
It's the other way around.
Yeah.
It's the other way around.
Okay. Okay, good. All right. Okay. Now let's go to bolt and nuts. Okay. So that's Alexander polynomial. Here, so it's so here's the definition which can be applicable to algebraic curves. So this is invariant of just abstract group which has surjection on integers. Okay, and from this data group and surjection over Z, you produce some model of a ring of Laurent polynomials. So how do you do it? So you consider kernel phi and analyze it. So that is kernel and so it turns out this Z, this group, cyclic group, acts a group of the morphism of this kernel, and it's also passes in the Billingization. So so this is this vector space has this automorphism. So therefore it's become a model of a group ring of integers, so which is the ring of Laurent polynomial, and so that's what we want to study. Now this so it's here the way it's formulated, it's surjection on Z, and this kernel actually is fundamental group of the covering corresponding to the kernel of phi, and so this is infinite cover. So and so what we have is a Billingization of kernel at the first homology group of its infinite cyclic cover. And since the cover is infinite, so it could be not finite, infinite dimensional complex. It may require infinite remaining cells. So, but or it could be finite. Okay, so that's something to keep in mind. Okay, so and I think so we've done with the slides, so let's go to the next. Oh, go to the next one. Well, so since this is this abilitization of this kernel of phi is model of a ring of Laurent polynomials, and ring of Laurent polynomial luckily is principal ideal domain, you can take cyclic decomposition, which has free part and which has a torsion part. So incidentally, so as vector space over Q, so that will be this quotient, this will be finite dimension if and only if there is no free part, if A is equal 0. Right, so that's if and only if. So right, so this order of this model of a principal ideal domain, which is just product of these factors, then that's the Alexander polynomial. And it's all, if A equals 0, it's convenient to put, so this, all statements go smoothly, to put that the delta of t is 0. Alrighty, okay. So now, most popular example is links, fundamental group complement to link. And so the homomorphism there on Z, you see the Alexander polynomial is not quite invariant of fundamental group. It's actually invariant of surjection on Z. Well, if you have a link, so there are several surjections. There are some preferred surjection linking, total linking number. If you have not, there is one surjection on Z, so it's become invariant of the knot group. So that leads to this classical notion of Alexander polynomial of link. Now, the main example in this talk is different. So X is algebraic surface. Well, as I say, I assume it's simply connected. And I assume it's simply connected. And this group may or may not have surjection on the Z. And so, but it's very simple issue to settle. And the next slide tells when it has surjection to Z and when you have the final example. So one thing remember that so for a long time people were focusing in the case when X is just projective plane. So then actually this fundamental group complement always has surjection into cyclic group. And but it turns out, and so that's what I want, another issue which I want to emphasize actually in this topic, I didn't talk much about it, that a lot of this theory of Alexander polynomial plane curve is actually can be extended to the case of a simply connected surface plus ample divisor. Okay, so that goes with this. Now that's now what I want to then understand, I already said, so that which polynomials can appear as Alexander polynomials of algebraic curves, and this second case. And first case is well known, goes back to Seifert at least. So you know, just this complete characterization which polynomials can appear, yeah, but for algebraic curves, so what helps a lot with the knot, so it's kind of soft problem as Gromov was called. Constructing links. So constructing surfaces and curves with interesting fundamental groups, in some sense, that's the center, that's the main hurdle. But that's not to say that even you have singular curves, it's particularly easy to find Alexander polynomial. That's another aspect of this problem. So there is Alexander polynomial of links, very well understood. This case is much less understood. Case of algebraic surfaces. Well, the overlap is very small. So if you just take these curves, so then there's a fundamental group of the torus knot PQ. But if you put here already more complicated singularities, like with two characteristic pairs, like if you look at the iterated torus knot, so then actually it's unknown if this fundamental groups of torus knot, iterate torus knot, except just for this case. So it could be fundamental groups of the algebraic curves. Yeah. So right. So just to, as I said, so that's the problem which I want to address. Right. Okay. Now this issue about homomorphism and cyclic group, as I said, it's quite simple. So if C is curved on simply connected surfaces, then you just so homomorphism and cyclic group, of course, factors through homology. So that's all this issue. So when the homology of H1 is non-trivial, So homology, of course, can be easily calculated. So basically, so here is precise formulas. So I just can tell. So if so here's an example. Maybe just good to keep in mind. So to see what's happening. So if it's C is class, a reducible curve class is divisible in Picard group by D, so then fundamental group is the cyclic group over the D, and one can run the same construction, so it doesn't have to be infinite group, cyclic group. At least once you have this surjection of non-trivial cyclic group, so you already get a non-trivial invariant. Okay. But if you have a non-divisible curve, okay, so then this theory is non-applicable. And of course, on P2, all divisors, except for classes of lines in each group fundamental group complement is trivial. All divisors are divisible, so you always have some Alexander polynomial. Okay. Right. Okay. So now there's what are restrictions on this Alexander polynomial? Which polynomials can come up with Alexander polynomials? So so this divisibility theorem. So here it's most general formulation with this. Most general formulation. So suppose you have a device which has two components, and so basically one can relate the relation with a global Alexander polynomial complement to the curve, and the complement to the curve to one of components of D inside the tubular neighborhood. Okay. So maybe it's best to go to the next slide where there is this picture, right? So here you have two components, right? So just on an algebraic surface, and here you have this divisor which is has many singularities. So you take tubular neighborhood, and so the first is divisibility result. The fundamental group of the complement to this D1 inside tubular neighborhood surjects on the global fundamental group, the complementary surface to Z1 and Z2. Okay. Well, so that implies this surjection of fundamental group, and that's compatible with this surjection of the group on the Z. So it implies divisibility. So Alexander polynomial, global Alexander polynomial divides Alexander polynomial the complement inside the complement inside the tubular neighborhood of one of components, one of the ample components. So the ample is very important. But again, just on P1, that's not an issue. So this ample is disappearing. And one can make it even more explicit. So if you have Pi is singular point of this divisor D1, then this Alexander polynomial complement tubular neighborhood just has such form. That's a fairly simple calculation. So and what's here? So here's this non-essential factor, which is easy. This factor is quite easy to control. And here it's product of Alexander polynomial of singularities, of rings of singularity. Okay, so that's the simplest way to see, for example, that. So and if you put this together, so you see that this Alexander polynomial, global Alexander polynomial divides this product. So, for example, we know that this polynomial is cyclotonic. Just very simple concept. Okay, so now here's the example to which one one wants to be very concrete. So that what can you do? So let's see irreducible affine curve WD with delta nodes, singularities in such form, or n-coupled cusps. So then this So the Alexander polynomial for node is t minus 1. Alexander polynomial for cusp is t squared minus t plus 1. So now, you see, a fine curve, its complement projective plane to either line in infinity or curve itself. So if you apply this divisibility line infinity, you get this result. You get this divisibility. If you apply the divisibility theorem to the curve itself, then you get such one. Because so this is product of Alexander polynomials of all singularities. Okay, and so if you just immediately you get, if you just play against both divisibilities, see that Alexander polynomials actually is trivial unless 6 is divisible by d. Very elementary, just because this is roots of this polynomial only roots of units of degree 6. Okay, so you see, just because we know that a curve has nodes and cusps, and by the way, there is no characterization of fundamental groups of the complement curves with nodes and cusps. So you're an Alexander polynomial, you already know it has such form. Okay, let's see, does it tell them? Okay. Okay. So now this, as I said, the delta is actually it's determined by the number of reducible components. So in this sense, it's a trivial fact. But the scarpa, that's the interesting thing. So that's the main problem. So that for curves with nodes and cusps, the question about which polynomials are Alexander polynomials is just essentially a question how big kappa can be. And that's what I want to focus on, how big kappa can be. Okay, that we were in the slide. All right, now that's, as I said, so one of these nice features of Alexander polynomial that it can be related to position of singularity. Now let me explain what does it mean. Okay, what does it mean is that basically, if you look at the cusp, indicators with nodes and cusp, you want to know if dimension of the curves of certain degree which passing through this cusp. So is it expected or it's not expected, or is it bigger than expected? Like this terminology comes like if you have 3 points, you know, so that if they are not on line, they are in general position. But if they are on line, in other words, dimension. So you see, if you expect that 3 points do not belong to any line. But if there is line, so there's actual dimension is bigger than expected. So there's difference between actual and expected dimension called superabundance. So the superabundance somehow measures this specialty of position. And it turns out this specialty of the position of singularities can be just extended for curves on every simple connected surface. Okay, so now the way this relation formulated sort of in technical way, so you try to tell multiplicity of each, you express in terms of position singularity, multiplicity of each root of the Alexander polynomial, of each root of Alexander. And turns out the roots of Alexander polynomial you can view as the character of fundamental group. That's homomorphism to C star. Any root has such form, and just and it gives and alpha is rational number, and so you relate to position singularity half of the roots. You know? So just you remember, and so the roots which you relate to position singularity, that's actually correspond to part of this Steenbrink spectrum in 0 and 1. So how the Steenbrink spectrum comes in? Because you remember, so after all this, the roots of Alexander polynomials, the roots of the local, roots of some Alexander polynomial of some singularity. I guess I didn't tell, so roots of Alexander polynomial of singularity is the, so it's roots of characteristic polynomial monodromy. And that's what Steenbrink was splitting in the groups, or actually Barchenko also, perhaps even first, the first Steenbrink. So, right. So, so it turns out, so one relates to position of singularity, so the roots which belong to this part of Steenbrink spectrum. Okay, and the point is multiplicity of this root corresponding to character can be expressed in such form. So to character of fundamental group, you can associate line bundle, and you can associate some ideal sheaf, which depends on singularities, so that multiplicity of root is the cohomology group of this this line. And so the key to obtaining these formulas, so just it's by relating this in calculation in terms of position linearity, dimension of the space of holomorphic one forms and cyclic finite. Okay, so so that may be a little technical. So that's so next slide describes some example, and that sort of so for the curve on simply connected surface, which has Fermi cusps. So the way you construct this curve, you take section, you pick up very ample line bundle, and construct section, pick up sections, and then you look at the zero section of zero set of this section of 6 power of this line bundle, and so it turns out it has it has cusps, singularities if sections are generically enough, and you can calculate.
Oleg, can we see what the theorem was?
You want to go back? Yeah, let's go back. Right. Yeah, the theorem was that the multiplicity of the root of Alexander polynomial corresponding to the character can be calculated from the following way. So character K kappa, you can associate line bundle, and with character, and so you can associate ideal sheaf in structure sheaf. So that that's the multiplicity of root. That's just the dimension of each one. So in the case of cusp, so all this. So A actually it's a certain multiplier ideal. You know, so I don't want to go into too much technicality, so kind of sweeping one under. Yeah, but it's some question asked, no?
So basically the character variety is the spectrum of
yes, yeah. That's right. But yeah, here somehow you won't actually restrict to polynomials. In other words, you look at only character which comes from which are factored through surjection onto Z of fundamental group. which was part of definition of Alexander polynomial. Okay. So maybe I okay. Now I'm looking at science. Just to be less technical, I tell you, if you have curve, so the classical example which one keeps in mind, so that you look at the curve of such form, right? So the example which next slide which I showed, it's generalization to arbitrary surfaces. So this example is risky. So you have F2 is generic form and of degree 2, generic form of degree 3. So if you look at the intersection of these two curves, so then at each intersection point you have a cusp. So here you have 6 cusps, and so you can calculate degree of Alexander polynomial just by well. So ideal A is just a sheaf of ideals. It's ideal sheaf which has such a quotient of structure sheaf by this ideal sheaf has a non-zero stock at the cusps and only, and so you know the bundle. So you get that the multiplicity of this root Alexander polynomial is superabundance of curve of degree 6 passing through the cusp. So in general you have so this is vast generalization of the statement that every single connected surface. Well, okay, so this is a relation between Alexander polynomial and geometry. Unfortunately, it doesn't tell very much about bound, because so it exists on the bound of degree of Alexander polynomial, because a question about the existence of the curves with nodes and cusps with specified position of singularities, it's a very difficult question on its own. So
can I ask you a question?
Yeah, of course, yes.
Hi. So this ideal sheaf, how does it tell about location of the cusps? For instance, you said that these cannot be collinear. So how the ideal sheaf doesn't care about the location, right?
No, it does, because you know it has. Well, I guess I can't write on the board. I said so. This is ideal sheaf. So the key property of it, which I didn't say. So if you take a quotient of structure sheaf by this ideal sheaf, you have a sheaf which has support exactly at singular point.
Correct. But then how does it learn that these three are not collinear, for instance? Or collinear?
Oh, it learns through these calculations, this H1.
Okay.
You see, this, so this this H1, it's difference between holomorphic Euler characteristic of this line bound minus dimension of H0 of this line bound, right? So holomorphic Euler characteristic, that's expected dimension, right? So holomorphic Euler characteristic doesn't know in which position, doesn't care in which positions are these points. But H0, that's dimension of the space of curves, and so which passing through through support, which containing support of this quotient structure sheaf by A.
Got it. Fantastic. Thanks. Yeah.
Okay, great. Okay. Right. Okay. So just going back. So basically, what the upshot of this, you get relation between two classical difficult problems, but you don't get the answer. Okay. It turns out there is a totally different interpretation of Alexander polynomial, which actually tells tell something about, which relates this question, this problem about degree of Alexander polynomial to another well-known problem. And the way it goes is as follows. So it turns out there is a relation between Alexander polynomial of plane curves and Mordell-Weil ranks of some trefolds. So how that goes? Well, turns out this. So you pick up this curve and then you look at the affine surface. It's a fine surface. So. So you can view this. You can view this equation as the equation of elliptic curve, the affine portion of elliptic curve of a function field of two variables, c of x, y. So so this is c of x, y. This is non-algebraically closed field. So you have by Neron and length theorem, so you have that this Mordell-Weil group is finitely generated group. Okay, so if you look, so the geometry of this trefold is actually quite interesting. So this is a trefold which has discrete, which is fibered over, which has mapped into P2, and a discriminant. So that a set of points where you have singular fibers. So that's exactly this curve, singular curve. So okay. So it turns out so the Mordell-Weil rank is just it's just expressed in terms of degree of Alexander polynomial. So then the question about the degree of Alexander polynomial becomes what is the what are possible ranks of Mordell-Weil groups of trefolds? Okay, so that well, you can show that a set of Mordell-Weil ranks of all trefolds doesn't I mean, it's of such type, which are fiber over P2. So it's not bigger than the maximal Mordell-Weil rank of elliptic surface. And of course there, so that there's this famous problem. So if the Mordell-Weil ranks of elliptic curves, elliptic surfaces are bounded. And well, I don't know. Some people think it's that ranks of elliptic curves are unbounded. On the other hand, so there's no example. So the largest known rank of a Mordell-Weil group of elliptic surface is 68, due to Shinoda, which is interestingly a surface exactly of that type. Where acceptances, so you take one, so this is show the surface for appropriate curve f of x, like x in power 360 minus 1. So this is in some sense, well, generalizations. So of course the question about Mordell-Weil ranks, it's well, it's for non-isotrivial family elliptic curve, for isotrivial. So this is actually very special elliptic curve. This is isotrivial. But even in this, with this restriction, so this question about distribution of Mordell-Weil rank, so just it is unknown. So here we have relation to other other geometric problems. So you see, I didn't emphasize just as enough. So you remember this divisibility theorem, that Alexander polynomial curve with nodes and cusps. It divides t squared minus t plus 1 in power kappa. I'm sorry. Well, it's equal in power kappa, but actually it divides link at infinity. So it divides So degree doesn't exceed d minus 2. So so this bound which depends on degree. You see, so another sub question for about is whether this another sub question is if degree of Alexander problem can be arbitrarily large. So and so divisibility gives only this bound depending on d, but this connection with the rank actually tells that degrees of Alexander polynomials are bounded independently of degree. And actually, this examples support sort of second guess, because the largest degree of Alexander polynomial, which we know, it's 8. So it's Alexander polynomial has form the largest known is t squared minus t plus 1 in power 4. It's achieved for some degree of degree 12, which has 39 cusps. So we have explicit construction, explicit calculation of Alexander polynomial, which incidentally done using this formula for position singularity. So 4 is the largest. So it's quite a bit smaller than Schroeder's 68, but sort of qualitative example. Well, okay, so this is a little long introduction, but it's good to popularize this topic. Now,
excuse me.
yes, yes.
So what happens if I change this polynomial u depending on u and v? So I consider another elliptic curve of u and
well, f is just let's describe curves with nodes and cusps. For example, yeah. So if I put here different thing. Okay. This is a very good question. Okay. So this is such form of elliptic surface. It comes because f. So this relation Mardel rank only when f has nodes and cusps. If you have more complicated singularities, so then you should look on Mardel ranks of abelian varieties of a function field. So an abelian variety is determined by local type of singularity. See, the point here that if you have curves and nodes and cusps, this abelian variety is just elliptical. So, but generally, that's where this string Jacobian comes in. Exactly. That's the point. All right. Okay. Well, so once this time is getting short, I think I'll try to speed up. So that's all right. So now I want just to understand put different restrictions, put different classes, just to see if Alexander polynomials of real curve, class of Alexander polynomial curves defined over reals, is somehow different than class of all Alexander polynomial all plane curves. Okay. All right. Well, and it turns out, well, don't know the answer, of course, but what I can do, I can get better bound than the for curves defined over real, and which and some assumption on the real points. And that's also good calculation. So we have better bound for the actually curves defined over reals, which do not have real points at all, empty curves. Okay, so then and then you get better bound, and actually its bound is sharp. You know, so that is what the example show. Okay, well, let me tell a little bit more of the details. So the way, there was one way I was just trying to get the divisibility theorem. So there is another way to get Alexander polynomial. It's from fundamental groups in terms of Braid Monodromy. Okay, well, let me remind quickly. So just because, the Braid Monodromy is just it's greatly studied from Washington and Dina, and also in case of real curves. Um, so, but let's see what we can get here. So let me remind Braid Monodromy. So instead of looking at fundamental group, one looks at another invariant representation. Another invariant of curve. Well, actually, curve together with the extra structure, which is you take this curve and that's these two segments. So that's my curve, with which I want fundamental group of the complement, and the way, so the way you define Braid Monodromy, you take generic projection of the curve on one plane, and you look at the fiber, you pick up a point in the base of projection. Well, you can think about this as XY plane. So then this is X coordinates, and this is Y coordinate. And so you project, so you get critical points. Right, so the points where the number of pre-images is less than the degree of the curve, and here generic base point of these loops in the base of projection. So the pre-images consist of different. So now the point is when you're going around this around each of these loops, so you can drag this vertical plane, and then you come back. When you come back, so your point may permute, but most importantly, you get diffeomorphism of the plane into itself. So once you choose trivialization of this vibration over each of these loops, so you get the diffeomorphism of plane with fixed point, and that's one of the definition of the braids. Braids are elements of the mapping class group of the plane, or actually disk, which fix point thing. Okay, so now if I take real curve, okay, now let me tell what I mean by real curve. So real curve is a curve which equation which has real coefficients. But a lot of attention was paid by real arrangements of lines. Okay, so when people talk about real arrangements of lines, so that actually means that each line is defined over rails. So here, arrangements also examples of these curves here. But here I wanted a product, so just product all equation will have real coefficients. So that means that actually arrangement, so each line may have a complex coefficient. In fact, there are real arrangements which have only finitely many real points. And that's what I'm particularly interested in those. Right? So it's all the different end of the spectrum that everybody is with attracted most attention. But anyway, so this is my base point. So, but with this one I want to be real. So then you look at this y plane over P, and so because curve is real, so these points they are distributed in special way in three groups. So some points will be on real axis. So these are points which are intersection of this y-axis with the real locus, with the set of real points of the curve. But y line of course is complex lines. So there will be two groups which have the same number of points, which are conjugate. Which are conjugate to each other, and so that right. So these are complex points of the real curve, right, which are not part of the real curve. Okay. And now, of course, the conjugation acts here. So these points are invariant, and then these points are interchangeable. And that's that's our most interesting aspect for me. So how conjugation acts, first of all, on this free group, and how it acts on the braid group, right, which is an automorphism of this free group generated by these loops. Okay, so right, okay, so right, so maybe should so these comments maybe should have made on previous slide, so that the way one studied Braid Monodromy, I said the homomorphism of fundamental group of the complement to the critical locus, this free group on the base, into braid group. And so this homomorphism actually can be is restricted, has important restriction. So if you put have a nice order on the generators of the group on the base, so then this product of this braid in this order will be generated of the center of the braid group. Okay, so that's fundamental relation. Which and so basically one of the things which I'm going to tell is that this one has for real curves one has refined of this relation. So now the action of the conjugation is actually quite not trivial. It reverses the it reverses order of generation, and so the action of the braid group by conjugation is the action of the outer automorphism of the braid group on the braid group itself. See, so by Dwyer and Grossman, there is actually group of outer automorphism per braid group is Z2. So there is only one automorphism, and this is actually the conjugation. That's I guess the Dwyer and Grossman don't think in geometric terms. It's pure algebraic paper, but it's an interesting geometric way to see this outer automorphism of Dwyer and Grossman. Now I'm confusing my order of my slides. Right, okay. So now that's now one can write so explicitly action of conjugation of the braid group. So here for this, so how one can choose generators. One should make choice of generators of the braid group. So this is not unique, but that's one of standard ways to choose generator. And so here you have the action of the braid group, just conjugation on the braid group defined explicitly. Okay, so so since time is quite short, so I'll start moving faster over here. What's interesting, so action of generators of braid group corresponding to these complex points, not on the real axis, they actually it's an operation which appears in Garside paper, classical Garside paper. So it's so conjugation. It can be expressed in two of these Garside operators. So and so now important property here, so that what we'll need to solve equations in a braid group, which involve this Garside operation. So this proposition would be viewed sort of some kind of analog, just of a description of elements of order 2. So, of course, this is not like if this operation will be trivial, so that will be sort of description of elements of order 2. But so this is different operation, and so that's sort of it's a solution of such equation. That's what we're doing. Okay, now refinement of Braid Monodromy. So now we are, so before we were looking on the y-axis, action conjugation on the y-axis. Now it turns out so these are critical points of the real curve, also distributed in special ways. So some of them will be real, and some will come conjugated. So therefore, just is so there are three canonical loops. One is coming in upper half plane, so one goes another only real points, and another is conjugate. Lower. See, so we see that there is some symmetry. The conjugation gives some symmetry in the. So in the Braid Monodromy representation, it actually passes the fundamental symmetry of the fundamental group. Okay, and what's interesting, so this symmetry sort of very much depends on the how critical value is distributed. If they are all real, so this part is absent. So,
so I'm saying that the conjugation gives some canonical predictor is passed by the real, the real part.
Yeah. There are symmetry in Gabriel, just yes, yeah. Okay, so now.
But there's nothing else that is canonical, just this three groups.
That's right. That's right. That's right. That's a good point. Well, you see, in the case of complex curve, there is only one canonical path that goes around all critical points, and that's what gives you this divisibility, this delta square relation. Because going around this path, and this is delta square, if curve is transversal to line infinity. Anyway, so the point was, so here you have this decomposition corresponding to these three loops. And so that's the relation which you have in the braid group. So this is this Garside operations. And yeah, okay, so particularly interesting case. So when this particularly interesting case when you don't have real critical values. So this real braid disappears. So now only two canonical loops, and they are conjugate to each other. So then you have such relation, and you want to solve this, and by this lemma which I mentioned. So you know that each of these loops here is the delta. So it seems that the complex conjugation sort of explains why delta square. Well. Why the square appears. So that's well, because of this conjugation. All right. Well, so since time is very short, so I won't take about the composition. I won't talk about the composition, other application of this ideas. So there is one, since time is very short, I'll just say quickly. So this is the composition of the Braid Monodromy of real curves. So it leads to some new surjections of the fundamental group, and I'll tell only so what is the new divisibility theorem. So maybe that's sort of the most important thing. So let's see be the real curve of even odd degree. Well, you see, such a projection doesn't have real values. Okay, so then right. So then you have such divisibility relation. Such divisibility relation. And you see, so here you have instead of d over 2. So you have estimation of degree with beta. So if you have curves of even degree, which has no real critical value, then you have such division. So that actually implies that also that this curve is empty; it doesn't have real point. So and this bound is interestingly it's sharp because like if you take curve of degree 6 with 8 cusps, so the Ittenberg and Difternoff told me that so there exists curve of degree 6 with 8 cusps with no real points, and but you have no real critical values. So then the multiplicity of this t squared minus t plus 1 for this curve is 2, and that's exactly what this, that's exactly what this fact is in this case. So at least for this relation is sharp for real curves of degree 6. Okay, well, so I'll stop here.
Thank you very much. Any questions? Me.
Where do we see real curves with empty real curves?
Oh, it's actually very okay. Let me write very simple. Like sex with 6 cusps. You're right.
No, I mean, where do we see it in real life? Do we see it in some physical phenomena? Where do we see it? I'm just trying to
Physical. Well, I don't know. It's
I'm
scale.
just trying to think of applications. That's all.
Well, just let me write this equation. So just at least one example to all this applicable. So this is sexy with 6 guys, which has no real which is empty. Yeah. But it's so my interest in looking at real curves and which have project no real critical values, it's comes with work with Shapiro, which I was mentioned, and he actually was motivated by physical equation. Most of his papers with physicists. So his studies of the Hurwitz space, subspace of Hurwitz space, space of meromorphic functions on Riemann surfaces, which has no real critical values. So those are benefits.
Another area that I like to apply is for cryptography. So to take all these very difficult like conjugation issues in the Braid group and make a crypto system out of it. But I killed myself because we developed an algorithm that statistically solved any equation in the Braid group. So it's not a always mathematical proof, but for crypto, if 80 or 85% is killing this. So I just wonder if maybe, because you mentioned this equation at some point, right? So I just wonder about trying to use it or trying to attack it. You didn't think about it.
I didn't think about it, but this is very no. I did see your paper about cryptography. I did see it. Yeah. But I couldn't connect. But perhaps well, maybe you explain a little better that. So
you shouldn't leave tomorrow. You should stay somehow.
Okay. Well, we'll find out. Okay. Yes.
I apologize if this is a naive question. So I've never seen this connection to Mordell rings. So where does it come from? Why? And for example, why do we add something like u squared plus b cubed versus what would happen if we add to f of x and y something like u to the 5 plus d to the 4?
Yeah, okay, let me tell you what's special. So this is isotrivial elliptic trifold, and it's trivialized on six-fold cyclic cover. Okay, so now you can show that this Mardell wave sections, they actually correspond to invariant sections of this trivial part, which base of which the six-fold cover. Now, so these maps from the six-fold cover to elliptic curve, it's actually very easy to understand because that's the maps from Albanese. And the key point is Albanese of six-fold cover is actually split. It's the product of two elliptic curves of exactly this form, u squared plus v. Elliptic curve has automorphism over the 3. Okay, so it's actually a very simple picture. You see all these Mardell wave sections because they come from map of some split abelian, well, in this case abelian surface. Yeah, so we just product to elliptic curves. Well, you know, in Schroeder case, you know, so you can interpret a Mordell wave rank of this Schroeder example, and it's which is u squared plus v cube is x 360 minus 1. You also can interpret of number of components in Jacobian of six-fold cover projective line branched over this point, 360 point. The number of times this elliptic curve, which has Marshall 3 appears there. This appears exactly 34 times. So 60 times. So there is this connection. I don't know if I explained it or not. So that,
Yeah, thank you. That's helpful.
So that's some picture there.
Any other questions from the remote audience?
But this link with the model value can be generalized to higher dimension too.
Not high dimension. Well, let me talk about high dimension. It can be extended to high singularities. Like singularity, like the toric UP plus VQ. Right. So then, you, as I said, you should look at the family of abelian varieties rather than just Mardell variety. Well, high dimension, you know, that's sort of another direction, you know. So if you have like just a projective space minus surface with isolated singularity, then actually you can look at the homotopic group here, PM. And it has Alexander invariant there. And so in this sense, there is high dimensional analog of this theory of Alexander. That I do not know how to relate to. Well, that's a good thing to discuss. You know? So that's another interesting project. Yeah. So that sort of high dimensionality is a different type.
So you said that it's in general hard to produce some interesting fundamental groups, right?
Yes.
That's the reason also why the degrees of the Alexander polynomials are like so small.
That's possible.
So
yes.
Is there like some?
But maybe they're just bounded. You know?
Yeah. So you think they are bounded, or you think they are?
I don't know. Well, I don't know what to tell you. I have this feeling to have. Yeah. Well, that would be very interesting. Yeah. But that's just because we never saw, you know, and never saw this curves with the high degree. And that's what this Martel variant kind of gives more credibility to this field. But you know, it counts for nothing. And really prove this.
Is there understanding of if you start deforming the picture, what happens to the Alexander polynomial?
Yeah, if you have complicated singularity, yes, there is surjection from the notebook, you know, it becomes more complicated, there is divisibility relation. So a more complicated fundamental group, the more complicated Alexander polynomial it has, in principle. But in fact, if it's realizable or not, that's another question. Yeah, but you know, like you have 6 Casperdal sextics, so you do know whatever you can degenerate into it, it will have Alexander polynomial. You know, at least that Alexander polynomial. Square minus. Yeah, there is this relation.
Any other questions? Thank you so much, Anatoly.
Yeah, thank you.
We have